Hello guys, and welcome to my three-part Three.js tutorial series, where we embark on an exciting journey to create immersive 3D experiences in your browser. To give you a taste of what's to come, I have prepared the following scenes to demonstrate the kind of stuff we will be creating. Let's take a look. Three.js is a versatile cross-browser JavaScript library designed to create and display 3D graphics in your browser. It's the tool you need if you're creating web applications with 3D visualization, games, simulations, and interactive experiences. I've personally used Three.js to create the video editor used for this tutorial. Three.js is popular among developers due to its user-friendly nature, extensive documentation, and active community support. This scene, though not exhaustive, covers essential concepts to help you become proficient with Three.js, empowering you to transform your original ideas into reality beyond just creating a solar system. In the first part of this series, we'll lay the groundwork by focusing on setup and developing an understanding of the components that make up a simple scene. As we progress to the second part, we'll delve deeper into the world of geometries and materials, and then wrap things up in part 3 exploring shaders. If you haven't worked with 3D graphics programming in any shape or form, all these terminologies probably don't make a whole lot of sense. But don't fret, they will at the end of this series. And without further ado, let's open up a terminal and begin setup. I'll be using Vite, which will generate a basic project for us and provide a local server with auto refresh, eliminating the need to manually reload the site after every change. Execute the command npm create Vite to start creating the project. I'm going to name the project Three.js project, and to keep things simple, I'll choose vanilla and JavaScript. Then navigate to the project folder using cd Three.js projects in order to install dependencies. And really, these are just Three.js and Vite. Note that Vite will be installed automatically as it is listed in the package.json file as a dependency. Once the dependencies are installed, execute the command npm run dev to launch a local server on port 5173. Also launch Visual Studio Code in the project directory. Now let's remove unnecessary files. Our index.html already contains boilerplate code. We're just going to replace this div with a canvas having an ID of display canvas, and this is where Three.js will render. We want the drawing canvas to cover the entire screen, and so let's update the style.css file accordingly. With these adjustments, let's now head over to main.js to begin the drawing process. And we'll begin by importing style.css, leveraging Vite's ability to handle CSS files. Vite will appropriately place the CSS file in the head tag of our index.html. It can also handle tasks like minification and preprocessing in case you're using Sass or less. Next, import the piece there is a stones, our Three.js library. Let's start simple, displaying a sphere on the screen. I'll write all the code and then provide an overview afterwards. Upon saving the code, you should be able to get this sphere displayed on localhost 5173. It's quite unremarkable at the moment, but it forms a nice foundation for our project. Now, let's break down the code into 5 broad categories. scene and camera, renderer, mesh, lighting, and animation loop. In a nutshell, you can think of the scene as the container for your 3D world. You append things to it using the add function. In the scene, you have a camera, lights, and the objects you want to draw. The renderer takes an image from the perspective of the camera and renders it on the screen. Let's delve into how the camera functions in our 3D world. The camera utilizes a concept known as a frustum. Imagine an invisible pyramid with its apex located at the camera's position and its base extending outwards. This pyramid encapsulates a bounded volume called a frustum. The boundaries of this frustum are marked by a near and far plane, with the near plane positioned closest to the camera. The frustum essentially acts as a window through which the camera sees the 3D world. The field of view determines how wide this window is, influencing the extent of the scene captured by the camera. A wider field of view encompasses more of the surroundings, while a narrower one focuses on a smaller area. Objects outside the frustum are not displayed as they fall beyond the camera's view. The aspect ratio ensures the content within the frustum is displayed proportionately to the screen. We set our canvas to fill the entire screen, and so in our case, the correct aspect ratio is the window's inner width divided by the window's inner height. Mismatched aspect ratios can lead to distorted or stretched visuals. So now we have a camera, but there's nothing to capture. Let's talk about how to create objects. And we can break this process into 3 steps. Step 1, we create our geometry, which can be thought of as the shape of our 3D object. In this case, we use a sphere since we are modeling planets. Step 2, we use materials to cover the surface of the object. This can be in the form of a solid color or even an image. That step is to combine geometry and material to create a mesh which represents the actual 3D object. This mesh is what you'll add to the scene. We shall discuss geometry and materials in greater depth in the next video. But for now, let me show you other predefined geometrical shapes at your disposal. Most materials in Three.js do not work without lights, and so we need to talk a little bit about lights as well. To explore the range of lights in Three.js, you have access to different types. Come, let me show you some of the lights available to you. First, there is the ambient light, representing light that has been scattered or bounced off surfaces rather than emanating directly from the source. It's used to simulate the overall environmental illumination. Ambient light alone might not be sufficient unless you're aiming for a dark environment, as it primarily outlines objects in your scene. For a more realistic touch, consider using a point light in addition to ambient light. This type radiates light in all directions from a single point, resembling a light bulb. Another option is the spotlight, akin to a point light but with a specific direction similar to a flashlight. Moving on, there is the rect area lights, emitting light uniformly across a rectangular plane, a useful choice for simulating sources like bright windows. However, our primary focus lies in directional lights. This light simulates a source infinitely far away, causing its rays to be parallel, closely approximating sunlight, making it particularly relevant for our scenario. Setting it up is straightforward. You simply define its position in space and specify a target point it goes through using X, Y, and Z coordinates. Materials within the scene can then infer the direction of light rays from the position and target points. Finally, we add the directional light to the scene. The renderer in Three.js is responsible for taking the 3D scene you've created and rendering it onto a 2D canvas, making it visible on the web page. In our case, we already created a canvas earlier with the ID of display canvas in our HTML, and it's the one we are going to use. It's important to make the renderer aware of the size of our canvas. The canvas we are using fills the entire window, and so we can use the window's dimensions. However, it's crucial to ensure that the dimensions have the same aspect ratio as the camera to prevent the scene from being rendered stretched vertically or horizontally. Let's create a function that updates the camera's aspect ratio and the render size to make the page responsive to the user resizing the window. The animation loop serves as a method to continuously update the scene, achieved through the use of the renderer.render function. This becomes crucial for maintaining site responsiveness or animating objects within the scene by making subtle adjustments to properties like position, rotation, and scale. The requestAnimationFrame function acts as a hook, linking the animate function to the browser's render loop, ensuring its recursive execution. We leverage this mechanism to call renderer.render and thereby update the scene iteratively. This concludes the introductory parts. Next, we delve into geometries and materials. My name is Francis for EclecticCodebase. Happy coding, and I'll see you in the next one.